All right, here we go, getting to work on the Work, Energy, and Kinematics final assignment. This is my solution video for this set of problems. So let's get to work. Mr. P. So number one, a winch lifts a 150 kilogram crate 3 meters upwards with an acceleration of 0.5 meters per second squared using a rope. How much work is done by the winch? So pretty straightforward question. Let's just get organized. The mass that we're moving around is 150 kilograms. We are going to lift it 3 meters straight upwards. So how about if I say that the starting height is 0 and the ending height is 3 meters with an acceleration of, so it's accelerating at 0.5 meters per second squared. And the question is, of course, how much work is done by the winch? So if we try to visualize this, some object here, there's an applied force that's coming from, in this case, I guess the winch. There's a force of gravity. And since it is accelerating upwards, the applied force is not equal to the force of gravity. It, in fact, would have to be larger than the force of gravity. So as maybe my first step, I'll just calculate that applied force since we're looking for ultimately the work done by the applied force. So, with that said, let me just kind of be able to scroll down a little bit. Let's see here, using up as positive, the acceleration is equal to net force over m, and of course that's an upward applied force and a downward force of gravity. I'll just jump right into mg, all of which is over m. So solving this for the applied force, multiply the m over, add the mg to get force applied. That means that the force applied is equal to ma, which is 150 times 0.5, plus 150 times 9.8. Grabbing my calculator. 150 times 0.5, add 150 times 9.8. So I'm getting 1545 for the applied force. 1545 newtons. And now that I'm looking for the work done by the applied force, you know what? Actually, hang on. I was originally thinking of kind of doing this H prime. I was thinking of going with potential energy at the start, but to tell you the truth, now that I have literally the applied force magnitude, I can actually just use force times distance since I know that it moves a distance of 3 meters. So I'm going to kind of change my approach there. I was originally thinking of doing it one way. So the distance is equal to 3 meters, just to kind of clarify that point. So if you want to know the work done by the applied force, the work done by the applied force is equal to the force applied, the distance over which it applies that force, times the cosine of the beta angle for the applied force, which is 0 degrees since it's pushing it upwards and moving it upwards. So 1545 times the distance of, what was that again, 3 meters, I think? Yeah, 3 cos of 0 degrees. So literally right now at my final answer of 4,635, I'll record that to just 3 significant figures. So how about if it rounds to 4,640 joules? That's it. Number one. So kind of a straightforward question to get us warmed up a little bit, but I know that these questions get more involved. In fact, I think starting right now with the second question, so let's get into it. Number two. A pitcher is on a baseball mound, which is raised 25 centimeters above the otherwise flat field at a location that's 18 meters north of where the batter is standing. Okay. The baseball, given mass, is thrown horizontally towards the batter, directly south, with an initial speed of that much. The center of the ball is that high above the surface of the pitcher's mound when released by the pitcher. Okay, so there's a lot of information here, like the mound, the height, where the ball is, the mass of the ball. Lots and lots and lots of organization, but just to continue reading into A, just to get a sense of what we're needing to do here. Part A, does the batter hit the ball if the center of the bat is that high above the ground when it is swung? The radius of the ball is also given. The width of the bat is given. So yeah, key to figuring out this problem is to be super, super organized. So I'll start maybe just with a rough sketch of what's going on here. So there is ground that is generally flat, but to be clear, there is a pitcher's mound. I'm going to exaggerate, I think, the height of the mound here, just for my own clarity here, that it is distinctly raised above the ground. So let's kind of get this in here. So from here to here, is the pitcher's mound, which I'd have to just peek back. It was raised 25 centimeters, so 0.25 meters above the otherwise flat ground. Okay, now the ball was thrown 42 meters per second, but it was 1.5 meters above the surface of the pitcher's mound. So there's going to be a ball here. I'm going to imagine the ball is being thrown to the left in this diagram. So it is 1.5 meters above the surface of the pitcher's mound, which of course makes it 1.75 meters above the otherwise flat ground. So let's actually really get into this now. Okay, so it's 18 meters north of where the batter's standing. So I'm not going to draw the batter. I'm just going to draw, there is a bat, right? So here is the bat itself. I'm just going to draw it in that position that it would be in when it's, swung towards the ball. Of course, the question is, does that ball get hit by the bat? So imagine this ball just being a projectile. It's going to be falling down, falling down, falling down. But of course, I don't know where it's going to go. Does it land, somewhere below? In fact, let's just kind of consider the possibilities. Does it go somewhere below and get missed? Does it not curve quite that much and also get missed, but because of being too high? Or we do have some kind of wiggle room here. There is, because of the width of the ball, the width of the bat, there is some obvious possibility here that the two will connect with each other, which is really to say the bat hits the ball. So we know that it was 18 meters horizontally away, so this is the starting position of the ball here, the bat's position there when it's being swung. We know that that is 18 meters. We know that the ball was thrown at a speed of 42 meters per second. So let's just kind of sketch that in here. The ball is thrown at 42 meters per second. It has a mass. I'll just sketch this in here. The mass of the ball is 145 grams. So I'll just rewrite that as 0.145 kilograms. Not sure if we'll need that at any point real soon. Certainly not for part A. The center of the ball, you got that. And then, of course, we have the bat's information. So the bat, just to switch colors to stay organized here, the center of the bat is 0.9 meters. So the center of the bat here above the ground is 0.9 meters. And it is the radius of the bat. Now, of course, bat and ball both start with the letter B, so I've already used just a B for ball, so how about if I say the full word bat here for it? So the radius of the, or no, it actually says the width of the bat. So how about if I take that width, thinking of it as a diameter, I'll chop it in half to get the radius of the bat. So the radius of the bat is going to be half of that 7 centimeters, so 3.5 centimeters, 0.035 meters, the radius of the bat. So I've got the mass of the ball. I better write the radius of the ball in here too. Radius of the ball, just using a B for ball, is 0.0363 meters. Again, just a quick conversion from centimeters there. And I think that's about all the information that we have given to us. So let's get to work. Part A literally is a projectile motion question, just with a lot of detail to it. So thinking of projectile motion, I will think of what the ball is going to do horizontally, and I'm thinking, since I know the distance that it moves horizontally, I know the speed that it's moving horizontally, since it was pitched horizontally, I can figure out the time it's going to take to get to the bat, and then I'll switch over to the vertical to figure out exactly where that ball is in terms of the height, in order to calculate or to determine whether the bat hits it or not. So in the X, it's going to move a distance of 18 meters, traveling at a speed of 42 meters per second. And since V is equal to D over T, it follows that T is equal to D over V. So 18 over 42, again, grab a calculator. I'll keep 5 figures on this one. 18 over 42 is 0.42857 seconds. All right, so we've got the time that it takes the ball to get to the bat. How high is that ball when it gets there? So in the Y, it started with an initial velocity of 0. It accelerates from gravity. I'm using down as positive. So 9.8 meters per second squared for a time of that 0.42857 seconds. So how far vertically does the ball fall? D equal to VIT, I'm not even going to write, it's just 0, so I'll just jump right into the 0.5 AT squared. So D is equal to 0.5 of 9.8 times that time of 0.42857 squared. Calculator again, I have that number in my calculator, so I'll use the full value since I have it so handy. 4.9 times that thing squared. Quick way to do it. And I get exactly 0.9 meters. So this is actually not even rounded off. And I did have that full number on my calculator from before. So 0.9 meters is how much it falls. Okay, so does the bat make contact with the ball? Well, okay, so the center of the ball, let's just kind of figure this out here. The center of the ball fell 0.9 meters. So that means that the height of the ball center, in fact, I'm going to have to steal a bit of room to work with here. So here's the ground. I'm going to exaggerate the size of these things just so I can visualize what's going on here. The center of the ball here is at a height above the ground that is going to be 0.9 meters less than the height that it started from. And if you recall, it started at a height above the flat ground of 1.5 plus the extra 0.25. So that's 1.75 in total, subtract the 0.9. So this is going to be, in fact, I'll just write that in here, 1.75 subtract 0.9, which is going to be 0.85 meters above the ground. Okay, so that's the ball itself. Now let's think of the bat. The bat, we were told, is at a height of 0.9 meters. So that center is a little bit higher than the ball. So let's just kind of sketch this in here. So the center of the bat is at a height of 0.9 meters. But we were told that it is thick, right? So the diameter of the bat, or the radius of the bat, is 0.0375. So let's just kind of sketch that in here. The radius of the bat, 0.0375 meters. In fact, I'll remind myself of the radius of the ball. The radius of the ball, oh right, I was using bat, full word for it. So the radius of the ball was given as 0.0363. 0.0363 meters. So the question is, do these positions overlap at all? Well, if you think about it, the top of the ball is going to be the height of the center of the ball plus the radius of the ball. So the top, okay, so the top of the ball is at a height of, I'm just going to calculate this, 0.85, 0.85 plus the radius of the ball, 0.0363. So that is how much? 0.85 plus 0.0363, yeah, 0.8863 meters, so 88 and a bit centimeters. The center of the bat is at 0.9 meters, but where's the bottom of the bat? Because you can see that if that bottom of the bat is like low enough, it will make contact. The bottom of the bat, in fact, let's switch to black for that kind of visual distinction here. The bottom of the bat is at a height of the center of the bat, 0.9, subtract the radius of the bat, so 0.0375. So calculating that on my calculator, 0.0375. So I get 0.8625 meters. Okay, so notice that the bottom of the bat here is below the top of the ball, which is here. So that tells me that they actually do make contact with each other. So in this question, what I was fundamentally asked to find, excuse me, what is fundamentally asked to find is, does the batter hit the ball? So my answer to part A is yes. All right, I'm just going to switch right into part B now to try to kind of get through these as quickly as I can here. So part B, which I'm just going to start working over here. Okay, so part B says, how fast is the ball moving when it arrives at the batter? Now, we could use conventional projectile motion kinematics to calculate this easily enough, but hey, it is a work energy unit, and I think I've got all of the information kind of in front of me from the previous part. This is going to be actually, I think, pretty straightforward. So how about if I just do, as far as the ball is concerned, it started at a height above the flat ground, if you recall, of 1.75 meters. So that's how high above the flat ground it was, 1.75 meters. And I've just found out that when it arrives at the bat, it is at a height, and I'm really looking at the center of the ball right now, it's at a height of 0.85 meters. So 0.85 meters. It started with a speed of 42, I believe, meters per second. And the question I'm being asked is, how fast will it be going when it has arrived at the bat? So I'll call that V prime. So rolling into this routine of M prime is equal to M plus the network NC, where there were no non-conservative forces doing any work to the ball. It just flew through the air, and of course we're even assuming there's no air resistance. So that means that K prime plus U gravity prime is equal to K plus U gravity. Should be a routine for us by now. So 1/2 mass of the ball, this is all mass of the ball, by the way, V prime squared plus mgh prime equal to the same in the original. So 1/2 mv squared plus mgh. And wouldn't you know it, we don't even need to know the mass of the ball for this. It drops right out. So in trying to find V prime, what I can do, I have options available to me. How about if I multiply the whole equation by 2 to kind of clear out those 0.5s? That'll be one nice thing. So multiply this by 2, I get V prime squared. I'm going to throw this to the other side of the equation. I'll try to condense this since I'm running out of space here. So multiply this by 2 gets me V squared. Multiplying this by 2 gets me GH, but 2GH, right? And then subtracting that over to the other side, subtract 2GH prime. So I multiplied everything by 2, and I also threw that GH prime to the other side of the equation. So that means that if I square root both sides of the equation, I will get V prime. So V prime is equal to the root of V squared, so 42 squared, plus 2G H that we started with, 1.75, and I'm just kind of running out of space here, so I'll continue here, minus 2G times the H prime, which was 0.85. Okay, that is supposedly all in the root, but just bear in mind that I've stretched out. That's not a division, that's just a continuation of what really should be a single line. But nonetheless, V prime is equal to, so let's get this in here, square root of the following. 42 squared plus 2 times 9.8 times 1.75, subtract 2 times 9.8 times 0.85, close my root, and get an answer of 42.2. 42.2 meters per second. So it didn't really gain all that much speed, but that's fine. I mean, it didn't even take very long, right? We already know that it took considerably less than a second to get there, so this is not really all that surprising. Okay, so for part C, there's another pitch, an identical pitch as described above. The batter hits the ball, causing the ball to rebound off of the bat, with the bat doing 300 joules of work to the ball. Okay, so here's how I'm going to handle that. I know that the speed of the ball as it just arrived at the bat was 42.2 meters per second. So if the bat then does 300 joules of work to it, it's going to be going even faster as a result of hitting the bat. it then basically becomes a projectile motion question again, and we should be able to use our conventional approaches to figure out the question here of how much higher over the pitcher's head does the ball eventually fly. So let's just kind of start with that impact with the bat. Okay, so in fact, let me just organize my thoughts here. I'll just use blue so it stands out. Okay, so ball gets hit by the bat. So let's just think of immediately before it got hit by the bat compared to immediately after it gets hit by the bat. Like, I'm just considering that impact alone for the moment. So just before it got hit, the speed of the ball was 42, and I actually have this on my calculator still. Above I wrote it to 3 sig figs. I'm going to record it now to 5 figures, just for a little extra accuracy here. So 42.209 meters per second, just before it got hit by the bat. Just after it gets hit by the bat, I wonder how fast it's going, considering I know that there was net work done to it by the bat. The net work done by non-conservative forces, in other words, an applied force from the bat, is told to me to be 300 joules. All right, now, the height of the ball is kind of irrelevant for this because, I mean, if I just consider immediately before to immediately after, whatever the height of the ball is, it's not changing. So what I can do is, for this part of the question, I can say the ending energy is equal to starting energy plus the net work done by non-conservative forces. K prime plus U gravity prime equal to K plus U gravity plus the net work by non-conservative forces. And the U gravity and U gravity prime, whatever they are, however high that ball is, because the height did not change, I can subtract that amount from the equation. So I'm not really crossing these out because it's, 0 in the usual sense, but whatever it is, it didn't change, so subtract it. All right, that makes it pretty straightforward to continue from here, because the ending, go back to blue here, the ending kinetic energy, 1/2 m of the ball v prime squared, is equal to the energy it started with, 1/2 m v squared, plus the net work done by the bat. So I'll just say net work by non-conservative forces, but that is that 300 joules. So if you want v prime, notice that mass does not drop out this time because there's no m in the third term here, the work term. So I do need the mass of the ball for this calculation. And I do have it. I'll have to scroll up to get it in a moment, but let's just solve this for v prime. I will multiply everything by 2, and I will divide everything by m in one shot. So here we go. V prime, in fact, I'm going to do this all in one shot. It'll be the square root of that. So multiply everything by 2. So 0.5 mv squared times 2 is just 1 mv squared. But I'm dividing by m, so that m will actually drop out. So it's just v squared is the only thing left from that term. Plus, multiply everything by 2, net work NC, and divide by mass. So something like that. So v prime is equal to the root of the starting speed, 42.209, which I square, plus 2 times the work done, 300, divided by the mass of the ball, and that I am going to have to do a quick scroll. It was here, 145 grams. So 145 grams, 0.145 kilograms. And that's all in the root. So, calculator time. Square root of the following. I've got that answer still sitting there, so I'm going to use the answer button. Square it, plus 2 times 300 over 0.145, close the root, and I get 76.93 rounded to 9. So 939 meters per second. Okay, so, and I definitely didn't give myself enough space here, clearly. I didn't give this a whole lot of thought, I guess. But it basically becomes a projectile motion question now. So the ball is now known to be going with a speed of 76.939 meters per second. And the question told me the angle that it was, launched from the bat at. It was 35 degrees above the horizontal. So 35 degrees above the horizontal. So completely a projectile motion question at this point, I can resolve this into components. So how about if I use colors here for maybe the x component? This Vx will be 76.939 cos, 35 degrees. And I'm just going to type that in, times the cos of 35, to get 63.0245. So I'll just round that to a 5 meters per second. And the vertical component, so this would be the Vy initially, is going to be 76.939 sine, 35 degrees. So keying that in, 76.939 sine of 35 to get 44.13. And there's a 0 there that I won't bother writing in, meters per second. Okay, now we know that the pitcher is horizontally, what was it, 18 meters away or something like that? Let me check back. Oh, yeah, 18 meters away. So in the horizontal, I know how far the ball goes. Distance is 18, not 42. I just said it. 18 meters. So since it's not accelerating horizontally, I can find the time it would take to get to the position of the pitcher, at least horizontally. So let's just do that quickly. So the time is d over v. That's just v equals d over t, solve for t. 18 over 63.025. So the time it takes to get there is 18 divided by 63.025. And so I'm getting 0.2856. And again, there'd be a 0 here that I'm not writing in here. Seconds. Now, meanwhile, what did the ball do vertically in terms of displacement? I mean, it started with that initial velocity of 44.13, but of course it accelerates down at 9.8 meters per second squared. It does that for a time of, that's 0.28, 0.2856 seconds. So let's calculate the displacement of the ball vertically. What will be the vertical displacement? Now, for the record, this is not going to quite be the answer because I'm going to have to factor in for the height of the person, etc. right away, but let's just calculate the displacement for a starting point. So we can say that the displacement is equal to VI t plus 1/2 a t squared. So that would be equal to VI, that was the 44.13 multiplied by the timing of 0.2856 plus the half of a. I'm just going to be quick and write that as subtract 4.9. And again, that time of 0.2856, which we don't forget to square. So, slogging that into the calculator, 44.13 times 0.2856, subtract 4.9 times 0.2856 squared to get 12.2. 12.204 meters is the displacement vertically of the ball. Now, of course, that means that the height of the ball is equal to the displacement of the ball plus the height it already was when it got hit by the bat. And we knew that to be, and we're just thinking of the center of the ball at this point, I think. So that was, oh yeah, right here. That was 0.9 meters, right? So the ball was already 0.9 meters when it gets, or no, actually that was the height of the bat. So that's actually not the number I was thinking of. The center of the ball I calculated to be at a height of right here, 0.85 meters. So that's the center of the ball at 0.85 meters above the ground already. So the height of the ball, I have to add that extra 0.85. Okay, so height of the ball is going to be 12.204 plus the extra 0.85 meters starting height that it already had. So adding the 0.85. So above the level ground, it is 13.054 meters. Okay, now the question said how high above the pitcher's head did the ball ultimately go as it passed over their head? Well, let's figure out how high the pitcher's head is. Okay, so the top of the pitcher's head is the height of the pitcher, plus don't forget that they're actually standing on this mound, so that's going to elevate them above the flat ground around them. So let's roll back here. The height of the pitcher is 170 centimeters tall, so 1.7 meters, plus the height of the mound, which I believe was 0.25 meters. All right, so the top of the pitcher's head above the level ground is 1.7 plus the 0.25, which of course is 1.95 meters. So if the ball is this high above their head, not above their head, above the flat ground, and their head is this high above the flat ground, we can subtract those to get the answer to this question. And I guess I am thinking of measuring to the center of the ball at this point. If you're tempted to subtract the radius of the ball to get the distance from the bottom of the ball to the top of their head, I would think that that's probably fine. But honestly, in a question like this, I think I'm able to revert to the simpler idea of the ball is just, it's a little tiny thing. The size of the ball is not important for this question. It was really important for the question of whether the bat hit it, but I'm just going to simplify and not worry about the radius of the ball for this calculation. Okay, so finishing off this, ball is therefore 13.054 subtract 1.95 equal to, so 13.054 subtract 1.95 is 11.1 meters above the pitcher's head. All right, so that's my answer. Number 3 says, a 75 kilogram person on a ledge, 23 meters above the ground, she grabs the bottom end of a 20-meter long rope that makes an angle that much from the vertical. Top end of the rope is attached to a sturdy support, and so we're going to swing in a circular arc, so we're bringing some circular motion into play, which is really nice. So let's kind of sketch this out. How fast is she moving at the bottom of the arc? Well, okay, so I don't think I need the mass for part A at least, so let's just sketch this out. She grabbed the bottom end of a 20-meter long rope. Okay, so there was a rope that was 20 meters long. Let's just call that L, the length of the rope. 20 meters long rope. Makes an angle of 25 degrees from the vertical. Okay, so there's a 25-degree angle to the vertical, and she basically steps off the ledge, etc., and as a result, she swings in an arc, kind of like a big pendulum, right? So she'll keep swinging, beyond that point. She'll swing all the way up, but let's just kind of focus on getting to this point, because at this point, she's moving with a speed that I'm curious to know, considering she started from rest. Yes. Okay, so this is a fairly standard kind of a question involving what arguably is just a pendulum. So here's how I'm going to do it. I'm not even going to worry about the height of the ledge and all that stuff. What I'm going to do is I'm just going to say, independent of all of that, I'm just going to say that since this is the lowest point she reaches, I'm going to designate that an ending height of 0. Which makes me wonder, what exactly was her starting height? So let's just call that h, but I don't know that value yet. Okay, but of course we can do some math, specifically some trigonometry, to figure that out. So have a look here would be one really nice way to do it. Let's focus on, I think we've even done this at one point in the past in a previous question. Have a look at this triangle that I'm outlining in red for you here, and realize that this is a beautiful right triangle. The length serves as the hypotenuse of the triangle, and how about if I designate this side of the triangle as just y, as a temporary label that will not be around for very long. So I can calculate y since I know L and I know 25 degrees. In fact, this 25 degrees has y as the adjacent and L is the hypotenuse, so let's focus on a cosine of 25. Cos 25 is equal to the adjacent, so that's what I'm just calling y, over the hypotenuse L. Therefore, y is equal to L cos 25 degrees, which is 20 cos 25 degrees. Grab my calculator. 20 cos 25, which is 18.0 18.126 meters. Right. So since this y value is 18.126, I can calculate the height above that reference level by realizing that let me just grab a color that's going to stand out, from here to here is also the length of the rope, right? Because the rope has not stretched or anything like that, so when she swings down to this point here, this also will be the length of the rope. So L. Excuse me. That means that the height here is L. In fact, I'll just write it in here. Height is equal to the length of the rope, and I'm specifically thinking of the green length that I visually drew in there. And of course, then we just have to subtract that value of y. So that means that the height is equal to L, the 20, subtract that y value of 18.126. So it is not quite 2 meters. 20 subtract that is 1.87. So this is h equal to 1.8738 meters. So how fast is she moving at the bottom of the arc? This is going to be a very standard conservation of energy calculation, so I'm going to do this quickly. The ending energy at the bottom of this arc is equal to starting energy plus the net work by non-conservative forces, but there were no non-conservative forces doing work. The tension was perpendicular to the motion the whole time. I think we've also seen that in the past, so hopefully that's clear. K prime plus U gravity prime equals K plus U gravity. The network is already gone. Starting kinetic energy was 0 because she was motionless at the very beginning. The ending gravitational potential energy is 0 because I've designated that as the height reference. So this simplifies tremendously. I can write 1/2 mv prime squared equal to mg starting height. Mass drops out of this one, and we can calculate v prime pretty nicely. V prime is equal to, multiply both sides by 2 to clear off the 0.5, and square root to clear off the square on v prime. So v prime is equal to root of 2g, and my height value of 1.8738. So v prime equal to, get that into my calculator, let's see, root of the following. 2 times 9.8 times that value, 6.06 meters per second, and I'll keep it on my calculator because I think I'm going to need that again right away, but so I do have it to more than 3 sig figs, but recording it only to 3. This is number 3, part B. What is the tension of the rope as she swings through the bottom of the arc? Wow, okay, I guarantee you a lot of students will just say, easy, that's the weight of the person mg and be done with it. That's not right, though, because let's not forget from our circular motion chapter that if you're moving in a circular path, and she is, it's not uniform circular motion, but she's moving along a curved path, then she is very much centripetally accelerating, including at that lowest point. So what is the tension of the rope when she's, swings through the bottom of the arc, when her speed is that value we just calculated? Okay, so it is not equal to her weight. In fact, let's visualize it as this. Yes, she has a force of gravity, and yes, she has a tension force, but she is accelerating upwards. The tension force is guaranteed larger than the force of gravity in this case. So I'm going to solve that with our usual approach here. I'll use up as positive. Her acceleration is, by the way, centripetal, but any acceleration is net force over m. And since I know her speed and length of the rope serves as a radius, I can write acceleration in terms of v squared over r, and the net force as a positive tension force, and a negative force of gravity, all of which is over m. The only thing I don't know in here is the force of tension, really, because force of gravity is mg. So, in fact, I'll be lazy and erase force of gravity and just put in mg. And as I've seen, or as I've said so many times, these m's do not cancel. So let's solve this for Ft by multiplying the m across. So force of tension is equal to, I'm multiplying the m across to be mv squared over r. That subtraction of mg, I will add mg to the other side. So plus mg, and that would isolate the force of tension, which I've already written on the left side here. So that should be good. So this is equal to m I forgot what her mass was, so 75 kilograms. Got it. So 75 times v squared, so I've got that 6.06. In fact, I have a few extra digits here, so I'll throw in a 0.3. And v squared over r, the length of the rope serves as a radius of the circle, 20 meters. Sorry. 20, there we go. Plus 75 times 9.8. So this will be the answer to this one. 75 times, answer on my calculator squared, divided by 20, add 75 times 9.8. So I get 870 rounded off to 3 newtons of tension force. All right. Okay, so part C says, at the lowest point, she releases the rope. How far, horizontally, does she eventually land from her starting location on the ledge? So far I've been able to kind of ignore that. I think I need a more complete picture now. So I will have to go back and see exactly what was going on here. So the person is on a ledge 23 meters above the ground. All right, so there's the ground, and there was a ledge. Okay, just kind of sketch this in here. That was 23 meters above the ground. All right, so this is where she actually started. And of course that rope was there as described, length L. So she swung down here and eventually reaches this point, at which point I know how fast she's going. She is going exactly to 5 sig figs, 6.0603. So let me even get that in here. So her speed, or really her velocity, horizontal, is known to be 6.0603 meters per second. And the question is, so how far horizontally does she eventually land from her starting location? So she's going to become a projectile, basically land, who knows, somewhere down here. And my job is to figure out exactly how far away she landed, horizontally. Okay, so that's the question. How far away horizontally from her very, very, very starting point is she? So clearly we can break this into two parts. Part one was kind of this just circular arc along this swing on the rope. And then part two separately will be projectile motion component. So, in fact, let's even call it part one and part two. So in part one, this is something I didn't have to calculate previously, so I'll do that now. I'll remind you that we did know, in fact, I'll just kind of sketch this in one more time here. We did know that there's this right angle. We knew that this angle up there for the rope was 25, 35, what was it? Oh yeah, 25 degrees. 25 degrees. So this horizontal piece of the triangle X can be calculated using sine of 25. So sine of 25 degrees is equal to opposite, which I'm temporarily designating X, over hypotenuse, which was the length of the rope, which was 20. So X is equal to 20 sine 25. Okay, so 20 times the sine of 25, which is 8.45. In fact, I'll keep an extra couple of sig figs here, so 24 meters. All right, so that's how far she went horizontally while still holding onto the rope. Then she lets go of the rope. All right, well, we've already determined above, and I'm not going to repeat calculations if I can reuse anything. We've already determined that she, in effect, dropped down. In fact, let me switch colors for contrast here. She dropped down, I'll just kind of color code it green here, that amount that I had previously been thinking of as this, height value of 1.87. 1.8738. So I know that that is 1.8738 meters, which means that basically her height at this point, the point that she releases the rope, is the 23 meters to the ledge, subtract that 1.87. So let's calculate that right now. This is 23 subtract 1.8738. 38, get that in there, that's fine. Okay, 23 subtract 1.87. 3.8. So she's at a height, effectively, of 21.126 meters above the ground when she lets go of the rope. So it now becomes straight-up projectile motion one more time. In the Y, now that we're in like part 2 of this projectile, or it is projectile motion, the part 2 of her movement, in the Y I can use down as positive. V initial is stationary because she was moving horizontally at the beginning when she lets go of the rope. So vertically, no motion at the very start of this part 2 movement. But she is known to have an acceleration of 9.8 meters per second squared because she let go of the rope. She's just in free fall now. She's going to displace down the 21.126 meters. And I wonder how long that's going to take. Yeah, because if I get the time, then I can switch back to the horizontal and figure out how far she moved in part 2. So, let's see here. D is equal to VIT, but with VI of 0, that's not worth worrying about, so 1/2 AT squared, which means that the time can be solved for. It'll be the root of 2D over A. So the time is root of 2 times D, 21.126, over the A of 9.8. So the time to fall to the ground after letting go of the rope is root of the following. 2 times, answer sitting on my calculator already, divided by 9.8. And I did forget a bracket in there. I'm going to slip that in right now. There we go. That should do it. 2.0764 seconds to hit the ground. Meanwhile, she's been moving sideways, so I'm just going to jump in over here. She's been moving sideways at a speed of that known value, 6.0603. And I know that as she moves as a projectile, I know how long that took now. It was the 2.07. 2.0764 seconds. So how far is she going to go? Well, it's just V times T. So 6.0603 times 2.0764 is how far? Multiply that by 6.0603. So 12 and a bit. 12.584 meters. All right, so she moves 12.584 meters in part 2, the projectile. In fact, just to kind of do that, she had already previously moved 8.4524 while still holding onto the rope sideways. So I'm ready to string this together to get a final answer to this question, because ultimately that's what we were looking for. How far in total, right? So in total, her X displacement, just kind of slip this in here, is equal to, or let's put it as displacement equal to, the two parts combined. So in part 1, she moved 8.4524, and in part 2, 12.584 for a grand total. Okay, so got that one on there already, so add 8.4524. So I get an answer of, oops, something went weird on my calculator. I'll just do that over. 8.4524, add 12.584. So 21, just barely over 21, 21.0 really, so I'm just going to call it 21 meters. All right, moving on to the last question, number 4. We have a block in the figure. A block of mass 5 kilograms specifically starts at point A with a speed of 15 meters per second on a flat, frictionless surface. So the horizontal surface is idealized, no friction. At point B, it encounters an incline, 15 degrees with a coefficient of friction 0.15, 2.2 meters long, and inclined at 15 degrees. I got that already. The block makes it up the incline to a second level frictionless surface. Okay, so there's only friction on the incline. The horizontal surfaces both have no friction. So part A, what is the work done by friction? Should be straightforward to do this one. We can just imagine the block at some point on the incline, doesn't really matter where. Thinking of the forces that would be on it when it is doing that, there'd be a force of gravity, which would be best thought of in terms of components. So there'd be a force of gravity component that is perpendicular to the surface, and another component, force of gravity, parallel to the surface. In addition, there'd be a normal force from the surface, and of course it is sliding against friction. So since it's sliding up the incline, friction will oppose that slide, so there'd be a second force pointed towards the bottom of the incline, or at least component. There's no force pushing it towards the top, just to be clear. A lot of students are tempted to put something in there, some kind of a force. There's nothing pushing up the top. It's only making its way up to the top because of the motion it had already had when it arrived at the bottom of the incline. So that's it for forces. The four vectors that I've drawn completely adequately do that. So if we want to determine the work done by friction in part A, that's all that we're really after here, what I can do is basically get right into it. I mean, I've got the distance that it moves because the length of the incline was told to me. So all I have to do is find the force of friction and then use the work equation, force times distance times cosine of the angle beta. So let's get right into it. In fact, I'm just going to do this directly. The work done by friction is what we're looking for. The work done by friction is the force of friction times the distance it moved with a force of friction, so that's only going to be the length of the incline, times the cosine of the beta angle as it pertains to friction, which is going to be 180 degrees since it's moving up the ramp, but the force of friction is towards the bottom of the ramp. Okay, so work done by friction. The force of friction itself is mu times the normal force. I'm going to save myself a step here. The normal force is going to be perfectly balancing off that component of the force of gravity perpendicular. So if you recall your physics of inclined planes, the normal force will equate to mg cosine of alpha, where alpha is that 15-degree incline. So I'm just going to write in here mu mg cosine of alpha. That there is the force of friction. In fact, I'll get rid of that. Times the distance it moves with friction exerting a force on it, times the cosine of the beta angle. So I think I know everything that I need to know in here. So let's just put the numbers in. Work is equal to the coefficient. Unfortunately, I do have to scroll back and forth. 0.15, I'll try to remember some of these numbers. 2.2, 50, okay. So 0.15 times the mass. No, that didn't work. I don't remember the mass. Oh yeah, 5 kilograms. 9.8. Cosine of 15 degrees, at least that's in the diagram, times the distance it moved up the incline, which was 2.2, yes, meters. Just want to double check that one. And cosine of 180 degrees. So don't confuse your beta angle, which is that angle between the force that we're considering right now, friction, and the motion. Don't confuse that with the alpha angle, which is nothing to do with the movement, nothing to do specifically with work and energy. It's just that angle of incline for an inclined plane. So I'm putting these numbers into our calculator, which I'm just grabbing here. 0.15 times 5 times 9.8 times the cosine of 15 degrees times 2.2 and basically times -1. In fact, I'm not even going to enter that. I just know it's negative. So I will say work done by friction is negative 15.6. And that's it for 3 sig figs. So 15.6, negative 15.6 joules. That's it. Part A. Moving on. Part B, what is the speed of the block when it arrives at point C? So at point C, maybe I'll just do a quick little side calculation here. I think I'm going to call this my height of 0 and realize that it ends up here at a new height that I'll call h prime, which I'm not given in the problem, but I can calculate it pretty nicely since I know this 15-degree angle and I know the length of this incline. So if you think of a triangle, specifically this nice right triangle sitting right here, then I can just calculate that height from the 15-degree angle in the 2.2 meter long incline. In fact, the sine, I'll just do it over here, the sine of 15 degrees is equal to opposite, which is what I'm actually calling h prime, over the hypotenuse of the length incline 2.2. So h prime is equal to 2.2 sine 15 degrees, which if I just do that here, 2.2 sine 15, in fact, before I do anything, because I have this number on my calculator, and I think I'm going to need it more in part B and maybe beyond. I don't remember if there's a part C. I'm just going to record a 5-figure version of this. So negative 15.619 joules. Okay, so that's a 5-figure, but I would call that my official answer to the question, to 3 sig figs. Okay, now I'm going to clear my calculator. 2.2 sine 15 degrees. I was just in the middle of finding that h prime. And I now see that it is 0.56940. I won't record, but there it is, the height in meters. So in part B, when we want to know the speed of the block at point C, what we can do is we can think of the energy that it ends with, up at point C, is equal to the energy it started with at point A, plus the net work done along the way by non-conservative forces. And friction was the only non-conservative force that did work. The normal force is non-conservative, but it was perpendicular to the motion again. So let's do that. The ending energy is the starting energy, accident, plus the net work non-conservative. So the K prime and the U gravity prime is equal to the K and the U gravity, and really I'm just going to say it's the work done by friction. Since I chose my height to be 0 at the starting level, I can cross that term out. It had no initial gravitational potential energy, but it had everything else in this equation. So 0.5 mv prime squared plus mgh prime equal to 1/2 mv original squared, plus the work done by friction. Don't forget we're trying to find v prime here, which is the speed at point C. So I will proceed to, let's see here, we'll multiply everything by 2 to clear off this 0.5. And while I'm at it, I'll divide everything by m. So let's do that. V prime squared, and I'll actually do this in 2 steps rather than one ginormous step. So v prime squared plus, now remember what I'm doing. I'm dividing by m, so that m will be gone, and I'm multiplying by 2. So 2gh prime equal to, multiplied by 2 clears the 0.5, divide by m, v squared, plus, multiplied by 2, and divide by m. So each and every term treated equally that way. Now I'll solve for v prime by subtracting this term to the right side and taking the root. I'll one-shot that. So the right side of the equation already had v squared plus 2 work done by friction over m. I'm now subtracting 2g height prime, all in a root. So v prime equal to, putting the numbers in, the starting speed, what was that? I don't even remember. 15 meters per second. So got that in here. 15 squared plus 2 times the work done by friction. Now, the work done by friction was negative, so let's not lose that negative sign. I'll use the 5-figure version of 15.619. So it is negative 15.619, all of which is over the mass m, which I have no memory of. It was 5 kilograms. There it is. 5. And then subtract 2 times g, 9.8, times the height prime, which I had calculated in green over here somewhere. It is 0.5694. 0.5694. All of that is in the root. So v prime is equal to, calculator time, square root of the following. 15 squared plus 2 times, and I'm just going to enter this as negative 15.619 divide 5, subtract 2 times 9.8 times 0.5694, close my bracket for the root, and get an answer of 14.4 meters per second. That's it for this recording. Catch you next time.